As we continue our unit on exponents, we're going to get now into writing and graphing exponential functions. So by the end of class, we'll be able to know how to write and also how to graph an exponential function. So we've already looked at what a linear function looks like. So a linear function would be the function in purple here. It forms a straight line. The exponential function is curved. And we'll talk about what happens there. But as we see that the linear function always follows a straight line, but the exponential one never drops below this x-axis here. And then it shoots up very quickly. You can see that it's up, shooting up towards infinity, just like the linear one is, but this one's shooting up a little bit quicker. Starts off slow, but then it slowly starts to increase and increase quicker and quicker and quicker. So that's something that is a characteristic of exponential functions, is their curve, and we'll talk about how we graph those and how we write the equations for them. So the one thing to notice here is when we have an exponential function, we have that exponent here. Notice we had y equals 2 times the x, whereas the linear was 2 times x. So we have a factor here for linear, but an exponent for exponential functions. We'll come back to this in a little bit, but let's get some information on the definitions of exponential functions. So an exponential function is one of the form a times b to the x, where a is not 0, because if it's 0, it's just going to be nothing over here. We talked about this as an exponential growth function. So really, we should say this is an exponential growth function when b is greater than 0. When b is less than 0, we're going to talk about how that is an exponential decay function. Okay, so exponential growth, b is known as the growth factor. It's what we're multiplying by. And it talks about how these are nonlinear functions. The graph of them is not a straight line. So as we look at the tables comparing the two, this linear function y equals 3x plus 2. We know 2 is the intercept, 0, 2. 3 is the slope. It means it increases 3 on the y for every 1 in the x. So notice as we go in the table, each of the y's increases by a constant amount. Exponential, this function 2 times 3 to the power of x. Notice as we increase by 1 on our x's, what's happening in the y's? We're multiplying by 3. So that's a characteristic on the tables of an exponential function. We multiply by a common factor each time. And notice this blue, the 2, the a, that is our y-intercept. So here we have our y-intercept. Here's where it crosses our y-axis. And 3 is our growth factor. That would be the b. So y equals a times b to the x is our equation, where a is our y-intercept and b is the factor. Whether it's a growth factor or decay factor, it's what we multiply by as we go from one y to the next. So as we take a look at this equation, y equals, we need to find our intercept first. When x is 0, across the y-axis at 8, so 8. And what are we doing each time? Looks like we're multiplying by 2 as we go from one y value to the next. So that's what I'm doing from 8, 8 times 2, x number of times. So that will be our equation for that, following that pattern of y equals a times b to the x. Starting at 8 on our y-axis, multiplying by 2 each time. Similar to our linear function, where we started at 2 on the y-axis, and we're adding 3 each time. Repeated addition, we use multiplication. Whereas when we do repeated multiplication, that's where exponents come into play. So why don't you see if you can create a rule for this function here, and restart the video when you want to check out if you are correct. Remember, things you got to find are y equals a times b to the x. All right, so the b value is what we're multiplying by each time as we go over one value in the x. So each time we move over 1 in our x, we're multiplying by 3. So our b value is 3. A is our y-intercept. Plug 0 in for x, and what do we need? So 0, it's at 27. So a is 27, b is 3. 27 times 3 to the power of x. So let's work on graphing. So let's say we have these values here. Let's just come up with some of these. Let's start at negative 3. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. So let's evaluate this function and see what the graph looks like. So 2 to the negative third is 1 over 2 to the third, which is 1 over 8. 1 over 2 squared, which is 1/4. 1/2, because 2 to the negative first is 1/2. 2 to the 0, that's 1. 2 to the first is 2. 2 squared is 4, and 2 to the third is 8. So remember, anytime we're graphing a function, whether it's linear or exponential, one of the simplest ways you can do that, if you don't remember any of the shortcuts or patterns, is just create a table and graph those points. So now we have our ordered pairs, negative 3, 1/8. It's going to be hard to graph, so just get it close. Negative 2 1/4. Negative 1 1/2. 0, 1. 1, 2. These get a little bit easier to graph. 2, 4, and 3, 8. Notice the distance between those is increasing. Now I'm going to complete this with a curve, because exponential graphs are curved, shooting up towards infinity. In this particular one, we're staying above the x-axis because no matter what we do, the numbers get smaller and smaller and smaller, but they will never get below 0 because we're just dividing by 2. 2 to a negative exponent, let's say it was 2 to the negative 100, it would just be 1 over 2 to the 100th power. It would be a very small number, but still above 0. So our domain is our x values. Our x values can be anything. So this could be all real numbers, because the arrows indicate that it goes forever to the left and to the right. And our range is our y values. Well, our y values never get below 0. So greater than 0. And they shoot up towards infinity. So that's our domain and range for that exponential function. Why don't you make a table for the next one? 3 to the x. Make a table, graph it, and identify its domain and range. Start the video when you want to check it out. I substituted my values of x in for the equation, and I got those values of y. I plotted those points on my graph, and I see x can be all real numbers, and y's are greater than 0 again. Notice as we compare it to the previous graph, this one shoots up quicker because we're multiplying by 3. It has the same y-intercept, 1. If we put it in the form a times b to the x, it's 1 times 3 to the x. Now let's compare these exponential functions. Let's take the parent function, y equals 2 to the power of x. Compare it with y equals 3 times 2 to the x and y equals negative 3 times 2 to the x. Let's take a look at this on Desmos. Here we have y equals 2 to the power of x. I've got my table created for that, and I see it graphed here. Let's take a look now at 3 times 2 to the x. Well, 3, as you recall, should be the y-intercept. So it should be crossing up here at 3, but it's multiplying by 2 just like the previous one was. So it should have the same curve to it. It's just the graph is just shifted up. As I zoom out, we see that the curve is the same. The graph is just shifted up. What do you think is going to happen when I multiply by negative 3? Well, that would be our y-intercept. It would be down here. Notice it curves downward. And for this one, our range is anything below 0. It doesn't get above the y-axis because we're taking what we had for 2 to the power of x, and we're now multiplying it by a negative 3, so all my values are negative. notice it's just a flip of 3 times 2 to the x. All the values are just reflected across the x-axis. Okay, so that's that effect that a value has. Affects the graph a little bit on where it crosses the y-axis. All right, let's take a look at exponential decay functions now. All right, so now we're going to take a look at the exponential decay function. It's the same format, a times b to the x, except this time b is less than 1. Okay, so b is less than 1. If we're multiplying by a number less than 1, the numbers get smaller. So that's going to be known as the decay factor. Whereas if b is greater than 1, anytime you multiply by a number greater than 1, you're growing. So let's look at this example here, and let's see why this is an exponential function. As our values increase by 1 in the x, what's happening in the y's? Well, they're dividing by 5. We're multiplying by 1/5 each time. So this would be an exponential function and a decay function because we're multiplying by 1/5 each time. Our y-intercept is 1, so b1 times 1/5 to the power of x. Notice we don't write dividing by 5 because it's easier to write multiplying when we're using the exponential form. So why don't you try that for the next example, see if you can get that function. So as my x values increase by 1, my y's decrease by 1/5 each time. So if I forget what that fraction is that I'm multiplying by, notice I'm dividing by 5. Dividing is the same as multiplying by the reciprocal. So my b value is 1/5 and my a is 10 because that's my intercept. So 10 times 1/5 to the power of x. So let's take a look at what this function looks like. Let's graph them. Let's put our values in, -3 all the way up to 3. Oops. When you make a table, you don't need all these values, but it shows the effect of the graph a lot when we show all of these values. So 1/2 to the -1/3. Well, we're dividing by a half 3 times. That's really 2 to the 3rd, which is 8. 1/2 to the -2nd is 2 squared, which is 4. 1/2 to the -1st is really 2 to the 1st, which is 2. Half to the 0, anything to the 0 is 1. Half to the 1st is a half. Half squared is a quarter. 1/2 to the 3rd is 1/8. Plot those points down, -3, 8. -2, 4. -1, 2. 0, 1. 1/2. 2 quarter, 3 1/8. So notice as we connect these with a smooth curve, it stays above the y-axis. Our domain still remains all real numbers, but notice that the graph is changed. With a growth function, we were starting small as we look left-right and increasing left-right. Here we're decreasing left-right. That's why it's known as a decay function. Notice our range are still greater than 0. So let's take a look at that parent function again and show that the effect that this a value has. Now when we're using the decay function times 1/2. So let's take a look at that on Desmos again. Okay, so here we have 1/2 to the power of x. Notice that decay function that we graphed earlier. You can see the table, the values decrease by a half. If we multiply 3 times a half to the power of x, we should have an y-intercept of 3. Notice it follows that same curve pattern, but it's just shifted up since we have a higher y-intercept. When we multiply by -3, when it's -3 times half to the x, it's going to cross the y-axis here, and you can probably guess what's going to happen. That blue graph gets flipped across, and so we have the same values, just the opposites, because we're multiplying by -3 instead of a +3. And here our range is less than 0. Okay, so decays get closer to our x-axis as we go left to right. Growth functions increase away from the x-axis. So exponential functions of the form y equals a times b to the x, and we took a look at how to write those equations and how to graph those.